example 2 wants us to solve sine of theta times tangent of theta is equal to sine of theta over the interval from 0 to 360 degrees. First thing we notice here is we don't just have a singular trig function, we have how many? 2, right? So it's not quite as simple as the one before it. Right? And here's where a lot of people go wrong. They want to divide both sides by sine. They really want to, okay? But you never want to divide by a variable because it can make answers disappear that should be there, because if there's something that makes the sine of theta work and you divide it out, you lose those angles. So avoid dividing by a trig function unless you absolutely can't. So what you do when you're tempted to do that, get it equal to 0 instead. So subtract sine from both sides and get it equal to 0. So we have sine of theta times tangent of theta minus sine of theta equals 0. And rather than dividing it out, factor it out. So treat it like a greatest common factor and factor it out to the front. So we have sine of theta times tangent of theta minus, if I take the sine away, this is a 1 right here. So if you can get it equal to 0 and get it factored, that is the best case scenario, because what that does is it now lets you take those two things separately and set them equal to 0, and now you will have a singular trig function in each. So once you get here, we're going to split it. We're going to say sine of theta equals 0 and tangent of theta minus 1 equals 0. And we're going to work each of those like they're two totally separate problems. Okay? Now the first one, sine of theta equals 0. Oh, and by the way, I guess now is a good time to point out, factoring only works if it's equal to 0. You're not allowed to factor if it's equal to, say, 3 or 5. You can only factor and split it up if it's equal to 0. Okay, and that's a mistake people sometimes make in this section. So you have to have it equal to 0 before you can factor it and split it into two different problems. Notice that this is a quadrantal, so technically we don't have a reference angle, but there are a couple of times where the sine equals 0. Can you name the first one?
0.
0 degrees? Yeah, the cosine of 0 is 1, and therefore the sine of 0 is 0. That sounded weird. Let's double check. Okay, it would be the point 1 comma 0. So you're right, the sine is 0 there. It also will happen again at 180, and it'll happen again at 360. So we've got 0, 180, 360. Those are our three values that theta can be. So that's going to be our question now. So I guess I shouldn't skip this step. I skipped it on the last one. Let me show it to you. Do you know technically how I get rid of this theta right here? I get rid of the sine. Technically, you take the inverse sine of both sides. But unlike regular inverse functions where they're built into the problem, you're not limited by all those quadrants and quadrantals. Anything can kind of go. So technically, we're skipping this step. And we've produced three possibilities. We said that occurs at 0, 180, and 360. But if you look back at that original interval right here, do you notice how there's a bracket around the 0 but a parenthesis around the 360? Okay, so that's what you were pointing out. We can't use the 360. So when we list these answers, we have to leave this one off because there's a parenthesis around it.
Because that means you can start at 0, but you can go up to like 359.
0.9999999. Right. And then we start repeating. So they've limited us. Now sometimes they'll put brackets on both, but most of the time the right side will have a parenthesis.
The first problem was a bracket.
Right.
Cool.
Okay, so we have tangent of theta minus 1 equals 0. So now we're going to come over here, we're going to solve it. We're going to add 1 to both sides and isolate the tangent of theta. And then we're going to take the inverse tangent of that. We're going to ask ourselves, what reference angle has a tangent of positive 1? 45. Okay, so we want to know where else does that happen. That's our reference angle. Okay, our reference angle is 45, and we want it to be positive 1. So we're going to use quadrant 1 and 3. Yeah, 1 and 3. So once you have your reference angle, it's not a quadrantal, you just move it into the appropriate quadrant. So we're going to keep the 45 for our first quadrant. And then to move it into the third, where tangent is also positive, remember we just take 180 plus 45, which is, isn't it? Yeah.
Plus 30. 45.
Hold on, let me try that again. 225 degrees. All right. So over here, on the left side, we got two answers, 0 and 180. And on the right side, we got two answers. We ended up with 45 and 225. For a total of, looks like we have 4 answers. We know that theta can equal 0, 45, 180, and 225.
We
So
have to put them in order.
you don't, no, you don't have to put them in order. It's okay. There they are. And we should check them, and you should check them back into the original. So what you should do, if you do this, is you should go through, and we'll start with 0. You should take the sine of 0, multiply it by the tangent of 0, see what that equals, and set that equal to the sine of 0, and see if that's true. And you should try that for all 4 of them if you have time. Always check your work as much as possible. And I believe all 4 of those do work out. You usually, unless you've made a mistake, you won't get extraneous solutions unless you square both sides during the process. And we didn't do that. So I'll pause right there and let you guys check them out. This is kind of neat. At this point, the book points out that if you tried to solve that equation in example 2 by dividing by sine of theta, that would have left you with only tangent of theta equals positive 1, and it only would have given you 2 of the 4 answers, 45 degrees and 225. You would have lost your 0 and your 180 degrees if you tried to solve it that way. So once again, avoid dividing by a variable expression. If you're ever tempted to divide by a variable expression, try getting it equal to 0 and solving it instead. Maybe by factoring or some other method. Okay, so let's take a look at another example. Here we have that the tangent squared of x plus the tangent of x minus 2 equals 0. We'd like to solve that over an interval from 0 to 2 pi. Notice that we've moved from thetas to x's and from degrees into radians. Unfortunately, this is not just simple. I can't just start solving for tangent and isolate it because it has a square on it. But it turns out the nice thing is it's already equal to 0, and it looks like it'll factor, right? Can we find something? It is a quadratic, something that multiplies to negative 2 but subtracts to positive 1. That would be positive 2 and negative 1. So it looks like we should be able to factor that. So we can take this quadratic right here, this trinomial, we can break it into the tangent of x in one parenthesis, the tangent of x in another parenthesis. We'll put a 2 here and a 1 here, a positive here and a negative here, and I think that will work. So I'll give you a second to look at that. So it was already equal to 0. We decided it would factor. Is anybody having trouble factoring the trig expressions now? Or remember when we went over that back in section 5.2? Yes. If you've forgotten, you can go back and look at those notes. Okay. Once we get it equal to 0 and factored, we can take it apart and take 2 different equations and solve them. So we'll take our first. We'll have tangent of x plus 2 equals 0. And we'll have tangent of x minus 1 equals 0. And we will solve those for tangent of x. So we'll isolate the tangent of x here, and we'll isolate the tangent of x here. And then we just need to figure out where those are. I'm going to skip over the left side for now because it bothers me that it's not on the unit circle. Does that make sense? So that means we're going to have to use a calculator to solve it, but we can do the right side just using our unit circle. What reference angle has a tangent of positive 1?
45.
It is 45, but since we're in radians, let's say that that's pi over 4. So there's our reference angle. That's the first thing you have to do. Then you have to move it into the appropriate quadrants depending on whether you would like it to be positive or negative. And I want it to be positive 1. So that means that it's going to be in quadrant 1 and 3. Okay, so quadrant 1 is good. We know that for quadrant 1, we'll just let x be pi over 4. And then do you guys remember what has to be true about quadrant 3?
1 more than the bottom.
Yeah, it's still going to be something pi over 4, but it's going to be 1 more than the bottom. So I think it's going to be 5 pi over 4. Okay, so that's what I think the answers are for this side. Any questions about that? Okay, now we want to come over and we want to figure out where does the tangent of x equal negative 2. I recommend always taking the inverse of the positive, not the negative. Okay, so we're going to find the reference angle by typing in, and we have to use our calculator because it's not on our unit circle. Just take the inverse of the positive. So tell me the inverse tangent of positive 2. And guys, please note, what mode should you be in? Radians. Yeah, we need to be in radians. We're going to find the inverse tangent of positive 2, and that's going to be our reference angle.
1.107.
Let's have it to 4 decimal places. 1.1.
Yeah.
Okay, 1.1071 radians, right? So, okay, now that's what it would be if it were positive and in quadrant 1. I need to now move those radians into the appropriate quadrants to make tangent negative. So I need to move that into quadrant 2 and 4. Okay, so let's talk about how to move things into those quadrants. Okay, this one's out, this one's out.
So you did 2 just to find like what the answer is, and then we'll figure out
The
like,
reference
the other
angle.
the other.
Right.
Yeah.
Always inverse the positive. That way you're guaranteed to have a quadrant 1 angle and you can move it wherever you need to. If you inverse the negative, it'll sometimes throw it into a negative angle and it'll throw it into quadrant 2, and then you're in trouble because you don't know what your reference angle is. So the goal is to use your calculator to find your reference angle. Then you can move it around other places as you need to. How do I move something into quadrant 2? Normally I would say 180 minus the reference, but this one I would just say pi, yeah. So for this one we're going to say pi minus the reference angle, which in this case is pi minus 1.1071. So that would be 2.0344. Alright, so take a minute and make sure you understand where that came from. We found our reference angle by inversing the tangent of 2. We found it to be 1.1071, but we want to know where the tangent is negative, so we moved it into quadrant 2 by saying pi minus that reference angle. Now we want to move it into quadrant 4, and instead of 360 minus the reference angle, we're going to say 2 pi minus the reference angle. So to move it into quadrant 4, 2 pi minus the reference angle will equal 5.1760. Yes? 5.1760. Okay. Now we've already rounded those.
I think it's 6.1.
You think it should be 6?
Because it's an 8 afterwards. 608.
I took the exact one. Like I didn't round it.
Yeah, see, it kind of depends on where you round. That was another thing that I wanted to talk to you guys about, is whether you round it or not. If you round the reference angle, it can change that final decimal, and that's nothing to worry about. If it's just your 4th decimal place that's wrong, then at this point we're not going to worry too much about it. But it is going to matter where you round. I usually store my reference angle, and that way I can use it to infinitely many, or I say that, 8 or 9 decimal places there, just to kind of be exact. It's up to you though. Another thing is when you check it, if you check the rounded answer, it's not going to check back as precisely as if you check the unrounded answer. So it's another one of those situations where keeping a bunch of decimals is probably in your best interest. Okay, we did get 4 answers. Let's talk about how to check them. It's a little harder to type that in. If you're going to type in tangent squared, you can put the square after the parenthesis, but a lot of times what I do, because it just seems like so much hassle, is I'll type it in like this. Let's say we're going to check 2.0344. I'll just type it in again. So that I don't have to worry about where my square goes. Okay. Now if I round it, it's not going to give it exactly to me. So everybody type that in, make sure you're in radian mode, and it's not going to equal exactly 0. What does it tell you if I type in my rounded answer? So here's what we were talking about. If we type in our rounded answer, and not storing all of the decimal places and keeping them, we end up getting 6.5914311 e to the negative 4. Do you guys know what that means?
That's a lot.
Zeros.
It's 0.000659114. So to the third decimal place, it is 0. Does that make sense?
Mm-hmm.
Okay, so it's showing up your rounding errors is what it is there. So it's throwing it into scientific notation, and it doesn't look like it equals 0, but it does, because that technically rounds to 0. So you have to be really careful when you check these. The more decimal places you keep, the more likely it is to go to 0. But even then, it can throw it off. But anytime you have something like e to the negative anything, that probably rounds to 0. So be cautious and be careful about that. All 4 of these actually do check out. If you guys want to take the time to do it, you may. Don't want to do that, do you? No. Okay. Well, we checked one of them, and we see how that actually rounds to 0. And then, of course, if you checked pi over 4 and 5 pi over 4, they would go exactly to 0 because those are unrounded. So just get in the habit of checking your work.
Can you turn the decimal places into like pi over?
Well, you could technically, but you shouldn't, because they would still be rounded before you turned them, and they still have just as much error.
Okay.
When you turn something into a fraction, that usually indicates you've never rounded. So you're discouraged once you've rounded from turning into a fraction for that reason, because then it looks like it doesn't have error, but it still does.